Bad things can happen by this design, but there's really only this kind of design because it's a finite amount of memory. So at some point, bad things are going to happen no matter what if a computer runs out of memory. So it's not that this was a poor decision. It's just sort of a necessary one given finite amounts of memory in a computer. But a heap overflow, so to speak, is whenever you call malloc or similar functions so many times that you just run out of heap space. And the heap somehow clobbers, that is, overwrites or touches the stack part of the computer's memory. By contrast, Stack Overflow, and some of you know this website if you've used it before from other programming classes, Stack Overflow is the opposite. When you call too many functions or you recurse accidentally infinitely many times such that the stack overflows as well. And in both cases, can bad things, heap overflow, stack overflow. I described this incorrectly. So heap overflow is when you actually overflow the heap and touch memory that you shouldn't up there. Stack overflow is when you somehow overflow the stack and touch memory that you shouldn't down there. So with that said, these are really just problems that can happen, and they're specific incarnations of what are generally called buffer overflows. A buffer, like in the YouTube sense, is just like a chunk of memory that in the case of YouTube stores like the next few seconds or minutes of video. But generally speaking, a buffer is just a chunk of memory that the computer is using for some purpose, be it the stack, be it the heap, be it an array in the computer. And so buffer overflows are what happens when you just have logical bugs in your code. But with these primitives now in mind, we wanted to conclude with the final revelations. And that's how some functions like these here work. The other thing in the CS50 library, besides the typedef for quote unquote string, is of course all of these functions. And we give you these functions because honestly in C, it is hard, it's annoying, it's painful, it's difficult to get user input correctly. It's very easy when you don't know how much the human's going to type to write buggy code when it comes to it. And indeed, it's really hard to store it correctly without accidentally having some kind of buffer overflow. So for instance, let me show you a program here that I wrote in advance called, let's say, give me 1 second and I'll pull it up. Nope, I'm going to go ahead and write this one from scratch. So let me go ahead and open a file called get.c, wherein I'm going to go ahead and mimic the idea of getting integers manually without the CS50 library. So I'm going to include standard io.h only. I'm going to define main as not taking any command line arguments. And then I'm going to do something like this. Give me a variable x with no value yet. And normally I would do something like getInt, but let me take that away. No more training wheels for getInt either. So let me just define the int x. Let me then just print out something like a prompt. And I'll just do x colon just to make it obvious to the human what we're waiting for. And now I'm going to use a built-in C function to get user input. I'm going to call a function called scanf, which sort of scans the user's keyboard for input. I'm going to scan it for an integer. So just like printf, I'm going to use %i because I expect an int. And then I want to tell scanf where to put the human's integer from the keyboard. It is not correct, though, to say x. Because if I say x, I run into the same swap problem. Scanf, no function, can change the value of x unless I pass it not by value, but by reference. So we're back to our ampersand friend. And now it has like a treasure map to the actual location of x and can therefore change it. And so now at the very end of this program, let me do something simple. Like let's just go ahead and print out with printf the value of x using %i as always, plugging in x, not ampersand x. This is now week 1 stuff. I want to print the actual integer value of x. So the only change here is that instead of using getInt, I'm now using this new function that as of today exists called scanf. So let me go ahead and run get, make get to create this program, /get. And let's go ahead and type in a value for x, 50, enter. And it just works. So it turns out getInt is pretty simple to implement. However, notice what does not work. If I type in cat, for instance, cat gets converted to 0. And meanwhile, getInt, recall, will reprompt the user. If a human does not type an actual integer, you get automatically reprompted. So that's one of the features we, for CS50, added to getInt just to make your programs more user-friendly. But otherwise, getInt is pretty straightforward to re-implement using scanf. Unfortunately, that's not true for strings. Because how do you know when you write your code what word the human's going to eventually type in, how long their greeting, like hi, is, if their name is David or Carter or anything else? You just don't know in advance how much memory you need. So how might we do this with strings? Well, let me go ahead and declare a string s. Although, you know what? There's no CS50 library, so we do char star s today instead. And that gives me not a string per se, but a pointer that will point presumably to a string. Ideally, I would use this, get string. But again, we've taken that training wheel away. So now that I have a pointer s, suppose I prompt the human for a value for s, just like before. Let me use scanf now and tell the user that I expect to read a string, %s from the keyboard, and store it in s. Now, this is subtle. I don't technically need an ampersand here, even though I did for an int, and I would for a float, and a double, and a long, and a bool, and a char. Why do I not need an ampersand in this story to pass by reference? Because s is, it's already an address. Again, strings are just special. Strings now are always addresses, so you don't need to additionally add an ampersand here. That's the only subtle difference here. But now if I go ahead and print out at the very end what the value of s is, using %s as before, this program looks like it's almost the same as the int version. But let's do make get. And OK, so this is not good. All right, so it doesn't like an uninitialized value. So let me make it happy. I said earlier to always initialize my variable. So let's initialize it to null so that at least something is there. That's your good default value nowadays. Now if I do /get, now we're good. And let me type in something like cat. OK, cat is not x. Well, let me try another word. Maybe it's just cat is wrong. Dog. OK, let me try David. It just doesn't seem to be working. Moreover, it's printing it as a 0. What logically, though, is the bug here? Scanf worked a moment ago for integers, but it's not working for strings. And it seems to be forgetting CAT. It's forgetting DOG. It's forgetting DAVID. Why? What's happening here? Think back to our yellow pictures of memory. When yeah. It might be reading just the null itself because s is being initialized to null. And what step have I forgotten from just like a few minutes ago? What did I not actually request of the computer? Like actual memory to store the CAT, the DOG, the DAVID, right? There's nowhere have I asked the computer for some amount of memory. And so technically, it might be reading it into some garbage location. And that's really the problem here. S is initialized to null now. And so in fact, it is printing 0 as null. But I'm not seeing any of the other letters because there was nowhere to put them. CAT, DOG, DAVID, because I didn't ask for 3 bytes, 4 bytes, 5 bytes, 100 bytes. There's no use of malloc. There's no use of an array. There's no memory allocated for anything other than the pointer itself. And this is where, honestly, life gets hard with scanf. Like, I could solve this problem in a couple of ways. Let me go ahead and do this. Instead of declaring s to be a pointer, let me declare s to actually be an array of 4 chars. And now, let me go ahead and recompile the code. So make get /get, and I'll type in cat now. That now works. Why? Well, I'm allocating an explicit array of size 4, enough for a 1, 2, 3 letters plus a null character. Here's where, to someone's question earlier, it turns out that in some context, you can treat arrays as though they are pointers themselves. C will sort of do the conversion for you. But for now, just assume that s is just an array of size 4. And if you pass it into scanf, that's like a treasure map that leads to those 4 bytes. So scanf can now successfully fill it with CAT, DOG, but let's try this again. Let's type in David. And here, OK, we got lucky, but I technically touched memory that I should not. And in fact, if I typed in a long enough string, and I don't think I could do it very easily, like without typing this thousands or hundreds of times, still OK. But you'll notice that it's forgotten the rest of it now. Right? So somewhere we went beyond the boundary of the array, and we just don't have enough storage space for that entire thing. So what do you do in your program? If you don't know how long the person's name or the animal name is going to be, what do you do? 40, 400, 4,000, 40,000? Like at some point, you have to draw a line in the sand. And that's why like getting user input is so annoying in a language like C. And that's why getString exists. What we do, if you're curious, is we look at the user's input, and we take baby steps. We look at it 1 character at a time. And every time we see another character, we actually call malloc again and say, no, I need more than 1 byte. I need 2. Oh, wait, they typed in 3 letters. I need 3 instead of 2. Oh, I need 4 instead of 2. And we have this crazy loop, essentially, that keeps asking for more and more memory, but by taking baby steps. And honestly, if you all had to do that in week 1, my God, like we couldn't even write hello world anymore. And so that's why these training wheels exist, at least early on. And that's why in higher level languages, like in Python, you don't have to do this at all. It just works as you'd expect. So what more can we do? Well, you'll see in problem set 4 this coming week, you'll see that there are, if I open up an example like this, phonebook.c, you'll see that you can manipulate files now that you have a vocabulary for pointers. It's going to be new quickly, but here we have an example of how I have a program using some familiar libraries here, but as I claim in my comment, this saves names and numbers to a CSV file. All of my examples thus far, I type in some words, I type in some names and some phone numbers, and they disappear because we only store them in memory. But if you want to store data in like a CSV file, comma, separated values, which is like a simple spreadsheet, like Excel and Apple Numbers and Google Sheets can open, you can actually do this yourself. So just as a teaser for this week, here on line 9, I'm using a new data type, not a CS50 thing, this is a C thing, called file. But if you want to manipulate files, you need to use addresses, that is pointers. So here is me creating a variable called file that's going to point to an actual file on the hard drive, on the server or your Mac or PC. fopen is going to be a new function you'll use that will open a file, and it will return effectively a pointer thereto in memory. The file name I want to open is phonebook.csv, and in this example, it's going to be append mode. It will keep allowing me to add more and more names and numbers to this file. Here's some old getString stuff, because I'm not going to reinvent getString with scanf. But down here is a slightly new function. It's not printf, but fprintf. And it turns out it's very easy to print things not to the screen, but to a file with fprintf. And it takes an additional argument. Instead of starting with the quoted string, you'll have to like say what file you want to write to. And fprintf will figure out how to get the bits into that file, passing in something like name, comma, number. So if I run this somewhat quickly here, let me do this. Let me pre-create a file called phonebook.csv. And in phonebook.csv, I'm going to create a temporary row here, name, comma, number, just so that there's something in this file. And now let me go ahead and do this and split my screen here. If I have phonebook.csv on the right and phonebook.c on the left, let me compile, make phonebook, which is the C version, /phonebook, and now I'm prompted for a name and a number. So I'll type in David, and then, for instance, +1 949, 468 2750. Enter. Oh, damn it. Bug. Pretend that didn't happen. I forgot to hit enter in the file. So let's do this again. If I run the program again, David, and +1 949 468 2750, enter, it's been saved now to the file. And if I close this file and I reopen code of phonebook.csv, you'll see that the file is persisting. And if I downloaded this to my Mac or my PC, I could double click the CSV file and voila, Excel would open up, or Apple Numbers or the like. And I've actually created an actual CSV file. If you're smiling because I keep repeating my phone number out loud, I would encourage you to call or text that number sometime. It might very well be an Easter egg of sorts. But via these functions here, do we have now the ability to write files, input and output. And among the goals then for this week, as we'll see, are to actually play with images in the spirit of something like Instagram filters or the like. And we'll introduce you, for instance, to a file format called BMPs, which, to come full circle to the start of class, are just maps of bits, but more than just single bits for white and black, but rather colorful patterns as well. And we'll give you images like this of the Weeks Bridge here across the river at Harvard. And you've run, after writing your own code in C and understanding how the data is stored in the computer's memory, you'll be able to apply your own Instagram-like filters to make things grayscale instead, or sepia in this case. You can even flip the bits around so that the thing is a mirror image. You can blur things further, or if you really are feeling more comfortable, you can even write code that finds the edges of the image and creates works of art like these. So all that and more in problem set 4. We will see you next time.